Hi, folks. My name is Q. First, I'd like to thank the organizer of this conference and this symposium. I'm very flattered to be able to talk about our research here. And today, I want to talk about when to retrieve and encode episodic memory. And I will start with this simple example. You'll notice that in this experiment, it's relatively clear when episodic retrieval encoding should occur. I'm starting with this one because many computational models of episodic memories are designed to capture human behavior in this sort of well-controlled setting. So in this pair-associative learning task that I made up, during the study phase, participants will see a sequence of novel cue associative pairs. Then later on, they had to recall the associate given the cue. So when should participant retrieve and encode episodic memories? Well, during the study phase, participants should encode episodic memory whenever they see a stimulus. And during test, they should recall whenever they're probed by a cue. But things can be more complicated. For example, say you're watching a two-part movie. First of all, we don't tend to recall for the sake of recalling information per se. Usually, we recall past information to predict what might happen in the future. And moreover, to process these two events, during part two, the agent needs to decide when to recall episodic memory about part one. And during part one, we also want to know when to encode episodic memory to support event processing in the future. And different from the pair-associative learning task I mentioned earlier, where information about when to encode and recall is given in some sense, in this kind of natural setting, figuring out when to encode and when to recall is an integral part of the task. So let's think about when should we retrieve and encode episodic memory. First, let's take a look at what data is available for episodic encoding. There's some intriguing data from Ben Yakov and others suggesting that event boundary is particularly important for encoding. The figure here shows hippocampal response while people were watching a movie, and this is the event boundary. And as you can see, hippocampal response peak after event boundaries, and this peak might be a neural signature of episodic encoding because the magnitude of this peak is bigger for events that were subsequently remembered compared to events that were subsequently forgotten for the just completed event. Overall, these results suggest that episodic encoding preferentially occur at event boundaries. Now, if that's the case, we would like to know why, why episodic encoding should happen at event boundaries. And moreover, why don't also encode episodic memory elsewhere? For example, we want to know if there's anything wrong with encoding episodic memory all the time. Okay, let me also give you an example about when do we recall episodic memory. In this study by Chen et al., participants viewed a movie in the scanner. And in the recent memory condition, people view the movie continuously. And in the distant memory condition, there's a one-day delay between the two parts. So they had to recall episodic memory from part one to properly understand part two. And in the no memory condition, sadly, participants never got to see part one, so they viewed part two directly. So for the first few minutes of part two, in the recent memory condition, participants still remember what happened during part one. That is, they formed a situation model during part one, which is still maintained during part two to help them to understand the ongoing situation. And in the distant memory condition, due to the one-day delay, the situation model about part one is no longer active during part two. So there's a gap in their understanding of the ongoing situation. So they have to recall episodic memory to fill in that gap. Overall, there's a stronger demand for episodic memory in the distant memory condition. The result shows that the level of hippocampal cortical correlation, which is a neural signature of episodic recall, was much stronger during the first 2 minutes of part two in the distant memory condition compared to the recent memory condition or the no memory condition. Again, we can ask at least two questions. First, why recall more in the distant memory condition, and why recall less in the recent memory condition? I want to know if there's anything wrong with recalling in the recent memory condition, or In other words, why recall more when there's a stronger demand and recall less when there's less demand? Is there anything wrong with recalling all the time? We like to understand and explain these patterns and results. And as you can see, one complexity in natural settings that's kind of particularly complicated is that different memory systems had to work together to solve tasks. And therefore, our approach is to build a neural network model with multiple memory systems. And once trained, it figures out a policy to use different memory systems to optimize its task performance. And similar to the logic of rational analysis, we can study the best way in which different memory systems can collaborate and solve these tasks. And that will help us to form hypothesis and explanation of why retrieval encoding happen at particular moments. So here's the outline of the talk. I will start by explaining the model, and then we'll study how does the model learn to use episodic memory in the service of event prediction. In this section, in the second section, I will fix the encoding policy to let the model selectively encode episodic memory at event boundaries. And then I will show you a simulation that explains why it is useful to selectively encode memory at event boundaries. And related to this, I will also show you why it is useful to selectively encode information with bigger prediction error. To prime you a little bit, one principle I'd like to show you today is that it's often useful to be selective both at episodic encoding and retrieval. And our model can tell us how to be selective. Here's a simplified diagram of the model, which has two parts. The cortex is a recurrent neural network. It's a long short-term memory network. It's just a recurrent neural network with gating. At a given moment, it observes the current state and predict what's going to happen next. It implements working memory and maintains information with its persistent recurrent activity. And it also implements semantic memory using its connection weights. The model also has an episodic module that corresponds to the hippocampus that stores episodic memories. And similar to other memory-augmented neural networks, these memories are represented as a list. And to encode a new episodic memory is simply copy the current cortical state or the hidden state of the recurrent neural network and append it to this list. And recall, the level of activation of each memory is related to its similarity with the current hidden state. And once we computed the level of activation for all memories, the model takes an activation weighted sum over these memories and add it back to the cortex. And critically, the model learns to control a gate on episodic recall. And this gate influences the level of activation for all memories, which in turn control when to recall. The model learns this gating policy with reinforcement learning. And specifically, the model gets rewarded or penalized depending on whether its prediction about the upcoming state is correct. And it can also say it doesn't know what the upcoming state is, in which case it gets 0 reward. And as I mentioned earlier, it's up to the model to decide what to do with episodic memory. We, as experimenters, don't specify that. The model's goal is to perform better at event prediction to maximize its expected cumulative reward. And when we train the model, it figures out a policy for setting the hippocampal gate that maximizes the reward. Okay, now let's talk about when to recall. In this section, we will fix the encoding policy and let the model to selectively encode episodic memory at event boundaries. And then we will see how does the model learn to recall memories to predict what's going to happen next. And we created a task that simulate or mimic the design by Chen et al. That I introduced earlier. And in particular, in the recent memory condition, we let the model to view a distractor event followed by 2 related events that correspond to the 2-part movie. And these 2 events are related in the sense that knowing everything about part 1 makes everything during part 2 predictable. So during part 2, the model has working memory and episodic memory about part 1 in this recent memory condition. And by contrast, in the distant memory condition, we will flush the working memory of the model by resetting the hidden state of the cortical network. So the model had to recall the correct episodic memory encoded during movie part 1 instead of the distractor. And In the no memory condition, of course, the model has no relevant episodic memory during part 2 because they never get to see part 1. So first of all, let me use an example trial from the distant memory condition to show you how the model handles the task. We used MVPA methods to decode the model's internal state by treating hidden unit activity as neuroimaging data. And the heat map here shows when and what features are decodable over time. And white means decodable. And these features affect the way in which this event unfolds. So concretely, so this feature might represent the current weather. Maybe it's sunny or rainy. And this feature might represent the location of this event. Maybe it's a restaurant or an airport or a coffee shop and so on. So as you can see, once the model observes the feature denoted by this green box, they often become decodable until the end of the event. And at event boundary, the model will encode an episodic memory. And since this is a distant memory trial, the model's working memory was flushed at event boundary, and I mean after the first event, so that at the very beginning of part 2, the model doesn't know much about the ongoing situation. Then we can see that the model recalled an episodic memory which brought back previously encoded information. We knew that because information about these features were decodable even before they were observed. Okay, to show you that the model uses episodic memory to support event prediction, let's look at the model's behavioral performance during part 2. So in the recent memory condition, since information about part 1 is still actively maintained in the model's working memory with its recurrent activity, so the model's performance on event prediction is perfect from the very beginning. And in the distant memory condition, initially, the model is completely uncertain about what would happen next because information about part 1 was flushed. However, the model's performance quickly approaches almost the ceiling level as the event unfolds because the model recalled the correct episodic memory most of the time. We knew that because its performance on the distant memory condition was much better than the no memory condition, where the model doesn't have an relevant episodic memory about the ongoing situation. Now, recall that at the beginning of part 2, in the distant memory condition, where there is a gap in people's understanding, there was a strong neural signature of recall. Whereas the neural signature of episodic recall was much weaker in the recent memory condition, where people has less demand to recall. In particular, it does make sense to recall episodic memory when there's a gap in my understanding of the ongoing situation. But the question is there anything wrong with recalling episodic memory when there's no gap? We simulated this pattern, and here I'm plotting the activation of different memories separated by target versus lure over time during part 2, which reflect the engagement of episodic memory. And we can see that in the distant memory condition, the model recalled episodic memory at the beginning of part 2. And the model in the recent memory condition, on the other hand, didn't recall nearly as much. Why is that the case? Remember that by design, models in both recent memory and distant memory condition have access to the same set of episodic memories. However, since models in the distant memory condition has a gap in their understanding of the ongoing situation, they were uncertain, which drove them to recall. And by contrast, models in the recent memory condition had very little uncertainty about the upcoming event. In this case, recall wouldn't provide additional information. In fact, it might hurt the model, since it might recall an irrelevant memory. And because of this, the model learned a policy to not recall if it think it already know the answer. Now, of course, besides uncertainty, many other things should influence recall decisions. For example, we found that if the cost of making incorrect state prediction is higher, then the model is more careful about when to recall. And we also manipulated the average similarity across events, which is related to how confusable the memories are. And we found that recall is delayed if memories are more confusable. But in interest of time, let me switch gear and talk about when to encode. I have been assuming that the model selectively encode episodic memory at event boundaries, partly because this is consistent with empirical evidence. But now let's critically evaluate this assumption and think about why it is reasonable to selectively encode episodic memory at event boundaries. So as I mentioned, there are two components of this questions. And I think the first point might be relatively clear now, as I showed you earlier. During part one, observed information will accumulate in the model's working memory. So it's really smart to encode what you had at the end of the event, since the memory formed at the end of at event boundary is more informative. But the more puzzling part of the question is if there is any advantage to selectively encode at event boundaries, or why encoding memory elsewhere is bad. And is there anything wrong with encoding memories, episodic memories, more frequently? To understand the potential problem of encoding elsewhere, we compared models with two different encoding policies. We let one set of the model to selectively encode event boundaries, and we let a second set of model to encode another episodic memory in the middle of an event. And now let's look at what can happen with the following toy example where the agent is looking at a sequence of information. So first you learn that the location of this event, which is this house, and then you learn the weather is sunny, and then you learn that this person is happy. If the model selectively encodes an event boundary, what happens is that it will store a memory like this. And later on, let's say you're looking at a different event. It's different because two of the features are different. The person's sad and it's rainy. And in this case, the model won't falsely recall this irrelevant memory, because once it gets to observe that the person's sad, it can detect this mismatch and reject this episodic memory. And that's great because these two events are different. Okay. On the other hand, let's say you do another episodic encoding in the middle of event one. And what happens here is that you get an additional episodic memory that's missing some information. It doesn't contain the information that this person's happy. And then there's a problem when it sees the second event. Again, when the model observes that the person's sad, it can reject a bigger memory because there's a mismatch. Then observe the location of this event, which is this house. And now for the smaller chunk memory, there's no mismatch so far. And there's an overlap. There's a match of location. So there's some risk of falsely recalling that small chunk memory. And this might bias the model later on to predict that the weather is sunny, which is incorrect. In general, this kind of small chunk memories are going to be more likely to get falsely recalled compared to the more complete memory formed at event boundary. Now we can be more quantitative. Let's look at task performance first. I showed you these results before, the model's performance when it selectively encodes at event boundaries. When the model also encodes another episodic memory in the middle of the event, the performance in both recent memory condition and no memory conditions are worse because it is more likely to incorrectly recall the small chunk memory formed from that irrelevant event. The performance in the recent memory condition wasn't affected because models in this case don't use episodic memory very much, as I showed you earlier. Again, we have seen this before. Models memory activation when it selectively encode at event boundaries. When the model also encode another episodic memory in the middle of the event, as you can see, the memory activation for lore was higher in the distant memory condition and the no memory condition. And note that the only difference between the two models is that when the model also encode in the middle of an event, there's these extra small chunk memories. Now, of course, many factors influence encoding decisions, including prediction error, reward prediction error, and people's prior knowledge, and so on and so forth. We haven't studied all of them, but let me show you a simulation that's related to prediction error. We think prediction error is particularly interesting since it's related to event boundary. I think Professor Gray will talk about this in greater detail, but in short, behaviorally, there's a memory advantage for both schema-congruent information and schema-incongruent information. It has been proposed that congruent information is remembered especially well because it fits better with existing schema, and incongruent information is remembered especially well because it triggers strong episodic encoding, since they evoke higher prediction error. And previously, McClellan and others have shown that neural networks can rapidly integrate schema-consistent information with its connection weights. So we are going to focus on the episodic memory part of the story. Now, what do we want to explain exactly? It's relatively intuitive that we should encode episodic memory for information that evoked high prediction error. However, the thing that's not so clear is if there's any reason why don't treat all information equally and encode episodic memory for everything to the same degree. For example, is there anything wrong with encoding schema-congruent information with episodic memory? To understand this phenomenon, our model went through the following pair-associative learning task. So 50% of the pairs are congruent with the model's prior knowledge, and the other half were incongruent. And congruency is defined or learned from past experience. Specifically, every Q has a congruent associate in the sense that they co-occur very frequently during model training. So our model will store these co-occurrence statistics in its semantic memory with its connection weights. For example, apple and tree co-occur very frequently during training. So during model testing, the model will think about tree whenever it sees apple. And paper and pen also co-occur very frequently during training. So after training, the model will think about pen whenever it sees paper. But during model testing, paper and soap co-occurred, which is incongruent, and that will evoke a big prediction error. In general, during model testing, the prediction error evoked by incongruent stimuli will be higher compared to congruent stimuli. Now, during model testing in the steady phase, the model observes the cue and then the associate, and then we can let the model to encode episodic memory when it experiences a big prediction error. And that will cause the model to selectively encode episodic memory for incongruent stimuli. Or alternatively, we can let the model to encode episodic memory for every stimulus in the steady phase. And finally, during the test phase, the model had to produce the associate given the cue. Here's the performance of the two models. In short, what we found is that models that encode episodic memory for everything was worse at incongruent stimuli. Why is that the case? Because when you encode everything, you have more episodic memories, and having more episodic memory means that there's more interference whenever you try to recall. So encoding everything can hurt your performance on episodic-based responses. And on the other hand, not encoding congruent stimuli is fine because the model can learn these congruent association with its semantic memory anyway. Now, there are many limitations of the current model, so we have an interesting to-do list. First, we have been defining encoding policy in a very narrow sense, which is, does the model takes a snapshot and store the cortical pattern at a particular moment? And when encoding happens, when episodic encoding happens, it always adds a new memory to the list of past memories. But in reality, there's a decision about whether to create a new memory or updating an old one. This is important for modeling the data on reconsolidation. And in the future, we want to work on simulations where the model learns a policy for how biased it should be towards pattern separation or pattern completion. Another limitation is that our model doesn't learn and manage multiple schemas. One hypothesis of what MPFC does is that it actively represents the ongoing schema, and our model doesn't have such a component, so it can only learn one schema at a time. And therefore, event boundaries were imposed by hand. We made the simplification so we could focus on questions about encoding and retrieval policies. We are thinking about incorporating ideas from the structured event memory model by our collaborator, Nick Franklin and Sam Gershman. And similar to our model, schema is represented in a recurrent neural network as well, but the structured event memory model uses multiple recurrent neural networks to represent different schemas. And it uses a latent calls model to decide which schema should be activated right now, or if it's useful to instantiate a new schema. And this mechanism can be used to perform event segmentation. And finally, the hippocampal component of our model is clearly a simplified version. And one exciting next step is to use a more biologically plausible architecture, such as the detailed model of hippocampus by Anna Shapiro. To summarize, today I showed you a neural network model with multiple memory systems. And one common theme of the results I showed you today is that it's useful to be selective. In particular, it's advantageous to selectively recall when there's uncertainty, and it's advantageous to selectively encode episodic memory at event boundaries. It has been exciting for us that we can train this model on some tasks, then the model can show us a reasonable way to solve the task using its memory systems. And this model taught us a few things that weren't completely intuitive. For example, when I started this project, it wasn't clear to me why encoding all the time is bad. Actually, many memory-augmented neural networks in machine learning do encode all the time. So perhaps our results have some potential implications there. Thank you for listening. I'd like to thank my advisors, Ken Norman and Uri Hasson, and my lab mates and our collaborators from various places. We would really appreciate any suggestions, comments, questions that you might have. Thanks again, and please enjoy the rest of the conference.